talk about the local graph, about the Grassmann graph, KQ2DD. So I will look at the local graph today. Yesterday, we established two tools we are going to use. The first tool was a tool that relates the global eigenvalues of different graphs with the local eigenvalues, the eigenvalues of the local graph. And the second tool was a polynomial that gives some intervals for this possible interval for the local graph. So I will go to use them first, and then I will start the proof how to characterize the local graph later. I cannot finish it today, but I'm sure we can finish it tomorrow. So let's get started. So how are we going to determine that the Grassmann graphs KQ2DD are determined by their intersection numbers? What we first will do is we try to find that the local graphs are the same as the Grassmann graphs, and then we use the Neumaier-Koolen time theorem to show that that's the system graph with the same parameter as the Grassmann graph KQ2DD, and D is at least 9, the diameter at least 9 is the Grassmann graph. So first we have to figure out what is local graph. And after that, we will go from the local graph to the global structure. But we don't know the moment we have the local graph whether the graph is geometric or not, because we will see that every edge lies in two delta cliques, so not one. And we say that a distance varying graph is a pseudo KQND if it has the same parameters as a Grassmann graph KQND. So, for example, a twisted Grassmann graph is in pseudo KQ2D plus 1D. So now we will use both tools that I developed yesterday, that any pseudo KQ2DD has the same spectrum as any local graph of a KQ2DD. We know exactly the structure of that graph, so we know also easily its spectrum. So for classical, for graph with classical parameters, the roots of the Terwilliger polynomial are easy to calculate. If you look at that paper or the paper, if you look at that paper, then the exact expression of P to X is determined in that paper I mentioned by me and Gavrilyuk. So the roots of the Terwilliger polynomial are beta minus alpha minus 1, minus 1, minus b minus 1, b times alpha. Okay, here I made a mistake. So it should be, okay, the Q should be in B. So I'm making a mistake. I'm sorry, this is completely wrong. This should be B times alpha times B to the power D minus 1. B to the power D minus 1 choose over B minus 1 minus 1. I'm sorry, this is very wrong. I'm sorry, that is very wrong. That is B times, because I was thinking in Q, because later on the B will be Q, so that is where the problems arise. So this will be B to the power D minus 1. What happened? So it should be B D to the power D minus 1 over B minus 1. Sorry for this confusing. And if B is greater to equal to 1, the leading constant of P, this Terwilliger polynomial, is negative. After the largest root is negative. That is what it means to say. So now, if we have pseudo Grassmann graphs KQ n, D, then it has classical parameters D, Q, Q, and Q times Q to the power n minus D minus 1 over Q minus 1. N is equal to 2D, then these parameters are D, Q, Q, Q times Q to the power D minus 1 over Q minus 1. And for n is 2D, the roots of the Terwilliger polynomial are Q times Q to the power D minus 1, Q minus 1 minus Q minus 1, minus 1 minus Q minus 1, and Q squared QD minus 1 minus 1. over Q minus 1 minus 1. So now we will determine the spectrum of a local graph. You think that we don't have enough information. But I will show that we are very, 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 very lucky. So we can determine the spectrum of the local graph. This is very amazing that we could do it. We could not believe it. So let gamma be a pseudo JQ2DD, and let X be a vertex of gamma, and delta X the local graph of gamma at vertex. Using the Terwilliger polynomial, we find that the non-trivial eigenvalues, that is the eigenvalues which are not A1, are Q squared times QD minus 1 minus 1. Oh, I missed something. I see. Okay, the first and the last eigenvalue here, they should be the same. They are the same. So that is a double root for this particular local graph. So for this particular Terwilliger polynomial, this is double root. So that means that there's only one positive eigenvalue and the rest must be negative. This is for the non-trivial eigenvalues. So I already had this. So we got one positive eigenvalue beside the A1. That A1 is clearly bigger than Q squared times this number. Or the other eigenvalues must be in the closed interval minus Q minus 1 minus 1. I'm very sorry today. Probably there are many misprints. I'm very sorry. I will repair them later. There are too many misprints. I'm really sorry for that. So we know that the valency of the graph is Q times QD minus 1 over Q minus 1. And the second largest eigenvalue theta of gamma satisfy, theta 1 of gamma satisfy, that is B1 over Q minus 1 with multiplicity M1, and that is Q to the power 2D minus 1 over Q minus 1. So that delta X has an eigenvalue minus Q minus 1 will multiplicity at least K minus M1 because M1 is smaller than K. And by the first result, we know that the minus 1 minus B1 over theta 1 must, and that is in this case exactly minus Q minus 1, must have multiplicity at least K minus M1, and that is this number. Q times Q to the power D minus 1 over Q minus 1 squared. So we have only about M1 other eigenvalues left. So let A1 and eta A1 must be an eigenvalue because the valency A1. So, and then we have eta 1 up to eta M1 minus 1. So I already mentioned that A1 is bigger than this Q squared times Q to the power D minus 1 over Q minus 1 minus 1. A lot of minus 1s here, I'm sorry. And so that means that the local graph must be connected with valency A1. Now we let eta be this number, Q to squared, Q to the power D minus 1 over Q minus 1 minus 1. And we say that it must have a multiplicity T. We don't know T is 0 or, so we allow T is 0. So then it's not exactly an eigenvalue, but we have to allow it. So then all the eigenvalues eta T plus 1 to eta M1 minus 1 must be in interval minus Q minus 1 minus 1. Yeah, that is what happens. So we have two equations, yes? We have many unknowns because we have, we don't know eta i's, yes? For I is T plus 1 to M1 minus 1. So we have a lot of unknowns. So it is very very amazing. But this is the first equation says the trace of the isochrony matrix of the local graph must be 0. And the second equation says the trace of the isochrony matrix squared must be K times A1. So and that can be expressed as the sum of the eigenvalues, yes, as you learned in linear algebra. So you have these two equations. Yeah, you say you have too many unknowns, yes. What do we know? We know that either i's are all at most -1, yes, and we have k minus m1, yes. So, but a1 is a positive number, so we can give a lower bound for t by the first equation, yes, because it should be the third term of the equation is negative, so if I remove that term, it should be positive, so we get a lower bound for t. Oh, but what does the second equation say? If you have that particular t, and we know that it has at most -1, so the second equation says that the second of the third term must be at least 1 times m1 minus t minus 2, or minus t, m1 minus 1 minus t, yes, times 1. So the first equation says that t should be not too small. The second equation says that if t is quite large, then the rest must be all -1s. So that is, we are very, very lucky. So it turns out that these two equations have only one solution. I mean, t is this, and all those ni's are equal to -1. Very, very, very lucky. I don't know why it worked, but it works. Don't ask me why it works exactly, because if you go for the bilinear Franz graph, it doesn't work like this anymore. So they behave very different. Maybe I can talk a little bit tomorrow about it, but I'm not sure I can talk too much about it. So the reason that the t has to be at least this number is that otherwise you get that the equation, the sum is less than 0. And then the second equation can only be satisfied if the unknowns are all -1, as I said before. So we are really, we know the spectrum of delta x for all x. For example, this means that gamma is 1/5. Yes, that the root, because they are all the roots of that Terwilliger polynomial. And yesterday, if the root corresponds with an irreducible tx model, and that is thin. So this means that gamma must be 1/5. If my conjecture of yesterday is true, then we know that gamma must be mu graph regular, and hence delta x must be co-S regular. So we don't know on this moment whether that conjecture is true or not, although I gave an indication that it is true yesterday. But on this moment, we don't know. There's no really written proof yet. So now we show that the gamma is mu graph regular. This was done mainly by Gavrilyuk. So using the same method as to show the existence of the Terwilliger polynomial, Gavrilyuk showed that the number row of common neighbors of 3 vertices I change to y, I change to z, such that the distance between x and z is equal to 2 satisfy that row is 2q mod q to the power d minus 1 minus 1 q minus 1. And if d is at least 4, then this is at least q squared. That's more than q squared. And then because 2q, if q is 2, that is same as q squared. Yes, so you have to be a little bit careful. You have to go to, you have to have something bigger than q squared. You have to have at least 2q squared to get something. So this shows that delta x is co-S regular with parameters k, a1 to q if d is at least 4. And Gavrilyuk also gave a similar equation for rho when x is attached to z. This somewhat helped to simplify the proof of Hayat, myself, and Rias. The last part of the proof can be, we don't need this last part of the proof from that is much simpler if you are in this particular. So now I will discuss the local graphs. So we will discuss the results by Sakana, Hayat, and others. So we need the S-clique extension of a graph. So the S-clique extension of G, a graph G, is the graph delta G obtained from T by replacing every vertex X of the every vertex X of T by clique X, tilde X with S vertices, such that any two vertices in X tilde in X tilde and Y tilde in Y tilde, they are adjacent if and only X and Y are adjacent in T. So if you take for every vertex and clique, and then you find all the edges if they were adjacent before, and no edges if they were not adjacent. So if tilde is the S-clique extension of T, then C tilde has adjacent matrix JS tensor A plus identity minus the identity times S, because S times M, because you want 0 on the diagonal. And JS is one matrix of size S, and IN is identity matrix of size. Then you can easily show that if C has spectrum of this, then the spectrum of T tilde is this. It's not exactly true what I say. It's if none of the theta i's are -1, then it's true. Otherwise, you have to add to the multiplicity -1 the multiplicity of -1 as an eigenvalue of T. S times -1 plus 1, -1 is still -1. Now let gamma be a Grassmann graph, JQ. Then any local graph, delta X of gamma, is a Q-clique extension of this square grid, Q to the power D minus 1 times over Q minus 1 times Q to the power D minus 1 over Q minus 1. And we know that the local spectra do not depend on only on the parameters. So for pseudo JQ2DD, we know that they have the same spectrum as the Q-clique of this grid. So our task is to show that they are the Q-clique extensions. And so now I will discuss the result by Hyatt and others. So then the main result in this subsection is the following result. Being co-S regular graph with this particular spectrum, where S is greater or equal to 2 and T is greater or equal to 1. Then if T is large enough, it's 11 S to the power 4, say, yes. Then gamma is the S-clique extension of the T plus 1 times T plus 1. But you need a lower bound for T, because if you look at the Strick-Hanna graph, that has the same spectrum as the 4 times 4 grid. So any S-clique extension of the Strick-Hanna graph has the same spectrum as the S-clique extension of the 4 times 4 grid. You need some bound. Whether it depends on S or not, we don't know. But we probably could replace the S to the power 4 by something S to the power 3. But I did not check all details. Yes. So we will mainly follow the proof by Sakana, Hyatt, and others. The method of Tan and others is probably an improvement of this method and will give lower bounds. I'm quite sure about it, but I did not look at the work out all the details. Not so difficult to do that, but I didn't. It's just that I don't have the time this week to do it. I need to prepare the talk. So, but you can, I think, replace the bound, the lower bound by S cubed instead of S to the power 4. Is my guess. It will help with the diameter. That makes also a difference with the the characterization of the Grassmann graph. And the method is a combination of the clique-Kloop method of Bose and others and spectrograph theory. We need both tools. We need, for example, that the local graph is walk regular and so on. And we need a bound on the clique order, because we don't know it is inside some graph or not, this graph. So we only give you the spectrum and say it's as regular. That is all what we are given. We are not given more. So first I will introduce the Hofmann polynomial. Who knows spectrograph theory know what I mean by this. So we have a regular graph with physique and it's connected with Atelier matrix A having exactly 4 distinct eigenvalues. That is what we have with the S-clique extension of the square grid. Then you can easily see that A satisfies the following equation: A cubed plus some constant times A squared plus some other constant times A plus a constant times identity must be the equal to K minus theta I over N times the O1. N is the number of vertices of gamma. This implies gamma is walk regular. That means that the definition of that is that for all I, a to the power I has constant diagonal. And it's true for the identity. It is true for A because that is all 0, the diagonal. It's true for A squared because it's K regular, so it is all K's on diagonal. And clearly it's true for the O1 matrix. Yes, so an A3 is a linear combination of these 4 matrices, so therefore A to the power 3 must have constant diagonal. And then you can always multiply by A and so on. If A to the power 3 has it, A to the power 4, A to the power 5, A to the power 6, A to the power 7, all have this. You can, for example, see that and there is a polynomial of degree 4 in A that is identical to the 0 matrix. If I multiply this cubic polynomial by A minus K times identity on left and right side, then on the left side I get an A to the power 4 and degree 4 equation in A. On the left hand side I get 0. And this implies that gamma is walk regular. So now let gamma be a graph with the same spectrum as the S-clique extension of the T times T plus 1 times T plus 1 grid, where S greater equal to 2 is a positive integer. Okay, so I make here a mistake. You cannot see the whole spectrum. Okay, but it has exactly 4 eigenvalues, and the smallest eigenvalue is minus 2, so we have to do 2 minus 2 times S plus 1 or minus 1. Minus 2S minus 1. Sorry, I made a mistake, so I should. So you cannot see everything. I'm sorry. I will repair it later. Sorry. Oh yes, I see. Okay. Yeah, the formulas are a little bit too long, so I have to figure out what to do with them later. So, but using the Hofmann polynomial, we obtain that we have this cubic polynomial. The exact, you can easily calculate what is the exact numbers yourself. And it means that if you look at the A to the power 3, the xy entry, you can get that it is the first expression if x is equal to y, the second expression if x and y are adjacent, and the third expression if where mu xy is the number of common neighbors if 2 vertices at distance 2, and lambda xy is the number of common neighbors of x and y as if they are adjacent. So you get these 3 expressions, and we will see that our graphical is regular, so we get that mu xy is constant and constancy. So now we look at the Hofmann bound. Yeah, you say it is. So we have a graph with the same spectrum as the S-clique extension of the T plus 1 times T plus 1 grid. Then for any clique C of gamma, say with order C, we have C is at most ST plus S. And if equality holds, then every vertex X outside C has exactly S neighbors in C. And the proof is you use the Hofmann bound. Yeah, you say, yeah, the Hofmann bound is for independent set, not for cliques. Okay, you're right. I agree with you. But if you apply the Hofmann bound for the complement of the graph, then you look at the independent set, the order of independent set, and then you can apply the Hofmann bound for the complement, and then you get the bound for the clique of the gamma. Yes, if you know the order of independent set of the complement of gamma, then you know upper bound for the clique of C gamma, and if that has this condition that every vertex outside the independent set has a constant number of neighbors inside the independent set, then we get that it is the rest here. It's C minus the rest here. Maybe I use now two C's in a different way. That's maybe not fantastic. Sorry. Maybe I should have told you that the C has order gamma or another letter. I'm sorry, that may be a little bit confusing because we have co-S regular and that has somehow also a C, yes? But later on, my C will be a particular number of, I mean, my C of the co-S regular graph will be a particular number. I will not refer to C. So, but yeah, a little bit awkward. So I already said the proof. So I said that you apply the Hofmann bound to the complement. So yeah, you have to look at the second last algebra and you can make it exactly precise. But I'm not going to do that. So tomorrow I will finish the proof. So on this moment we have some spectral observations for the graphs, like we have the Hofmann bound, we have an upper bound for the clique order, we have walk regularity, and so on. Yes, and tomorrow I will use the clique method to show that they are really determined by their spectrum if T is large enough. T is in at least something like S to the power 4. Yes. Okay, that is where I stop for today. I'm sorry for the many mistakes today. Okay, thank you.
So for other classical distance regular graphs, has anyone worked out the post-spectral graph of the local graph?
It is quite difficult if you don't know. So usually we don't even know the spectrum of the local graph. For example, the bilinear form graph by BILQDD. For Q is 2, we can get the spectrum of the local graph. But for Q larger or equal to 2, I have no idea. We get some restrictions, but I don't see how you can get the spectrum in that particular case. And so in this particular case, we were very lucky.
I wonder if luck comes with classical. And that was my question. You always get
but the bilinear form graph is a problem maker.
I have a question, Jack.
Yes.
So part of the luck that you're talking about was that the Terwilliger polynomial had a double root.
Yes.
In this case. What about the other graphs with classical parameter?
I mean, they can have a double root. For example, the bilinear form graph T times Z over GFQ, that has also a double root, for example. Right, and of course the antipodal Johnson graph and the antipodal half cubes. I think that they have all double roots.
Well,
but I think those are the only ones we know of.
Thank you.
Thank you.